Welcome to today's deep dive. It is Thursday, May 14th, 2026, and we're doing our daily cybersecurity briefing. The mission today is pretty simple. We are unpacking three critical stories, giving you clear takeaways and, the actual practical impacts without just drowning you in information overload.
Right, because there's a lot of noise out there right now.
Exactly. And, when you move into a new house, the very first thing you do is change the locks, right? You just assume that holding the physical key means you control the perimeter. Like, the logic is totally binary. You have the key, you are secure.
Yeah, physical control equals absolute security. I mean, at least that's the comforting illusion our industry has kind of leaned on for decades.
But so what if the house itself has a hidden underlying blueprint? What if someone can walk up to your front door, slide a weirdly shaped piece of plastic into the mailbox, and suddenly the walls just dissolve?
Wow, yeah.
You're standing there holding your high security key, but the house is completely open. And that is exactly the architectural nightmare we're dealing with today in our digital infrastructure.
It really is. And the overarching narrative of today's briefing is really about the hidden dangers of legacy trust.
Right.
Whether it's an 18-year-old remote code execution flaw, or trusting local recovery environments, or, relying on outdated certificates, today's stories show what happens when the foundational elements we explicitly trust just turn against us.
Yeah, and by the end of this deep dive, you will understand exactly where your infrastructure might be vulnerable today and what actionable steps you can actually take immediately to secure it. So let's start with the physical perimeter, looking specifically at Windows.
Okay. Yeah.
There are two new zero-day vulnerabilities making massive waves right now. They were disclosed by a researcher who goes by the name Chaotic Eclipse.
Or sometimes Nightmare Eclipse.
Yeah, Nightmare Eclipse, exactly. And they've codenamed these bugs Yellow Key and Green Plasma. Now, Green Plasma impacts the Windows Collaborative Translation Framework, but Yellow Key is the one that's really setting off the alarm bells for Windows 11 and Windows Server 2022 and 2025. And Chaotic Eclipse actually called this, quote, one of the most insane discoveries I ever found.
And honestly, looking at the mechanics, that is not an exaggeration.
Yeah.
I mean, Yellow Key essentially acts like a backdoor built directly into the Windows recovery environment, or Winery.
Right, and Winery inherently holds the keys to the kingdom because it requires, deep, unrestricted system privileges just to run diagnostics and repair core OS files.
Yes, yeah.
So how is a researcher abusing that baseline trust? Like, what is the actual execution path here for an attacker?
So the attacker drops specially crafted files, specifically these FSTX files, onto just a standard USB drive or an EFI partition.
Okay.
They plug that USB into the target machine, and they force a reboot into the recovery environment. And crucially, they do this even if the drive is fully protected by BitLocker encryption.
Wait, really? Even with BitLocker on?
Yeah, even with BitLocker on. Once Winery loads, they basically just hold down the CTRL key, and the system drops them straight into a root command shell.
Okay, hold on. I need to push back on that sequence because how does an untrusted USB drive magically bypass an encrypted environment? I mean, BitLocker is supposed to lock down the volume. What are those FSTX files actually doing?
Right. So to understand that, we really have to look at the underlying mechanism that security researcher Will Dorman pointed out.
Okay.
Those FSTX files are tied to a legacy Windows feature called transactional NTFS, or TXF.
Ah, TXF. Okay.
Yeah, Microsoft introduced TXF way back in the Windows Vista days. And the goal was to treat file operations the way a database handles transactions. So like if you're installing a massive software update and the power goes out halfway through, TXF ensures the system doesn't corrupt.
Right.
It either completely succeeds or it rolls back to the previous safe state.
So it's basically an integrity mechanism. It logs the changes so it can just undo them if something fails.
Precisely. But here is the architectural flaw that Dorman highlighted, which is the real buried lead here. The attacker creates an FSTX directory on the untrusted USB volume. When Winery boots, it sees this pending transaction log and it attempts to process or, replay it.
Okay, so it just blindly trusts the log.
Right. And the catastrophic failure is that TXF allows a transaction originating on one volume, so the USB drive, to modify the contents of a completely different volume, the Winery partition.
Wow.
Yeah. The attacker's transaction specifically deletes a file called winpesh.ini on the recovery drive, and that alters the execution flow and pops that command prompt.
Oh, man. Okay, so let's unpack this. It's like a guest in your pool house somehow rearranging the furniture in your locked main house without ever touching a key.
Exactly.
The rollback safety mechanism itself is being weaponized to cross boundaries that should be hermetically sealed.
That's a perfect way to visualize it. It completely breaks the fundamental rule of file system isolation. And, complicating matters is the human element of this disclosure.
Oh, yeah, the drama.
Chaotic Eclipse is currently in a very public, very hostile feud with Microsoft over how their previous bugs were handled.
Yeah, the drama there is intense because last month they dropped 3 0 days. Bluehammer, Red Sun, and Undefend. Microsoft patched Bluehammer, but apparently they addressed Red Sun silently without giving the researcher any credit via an advisory.
Which never goes over well.
No, not at all. Chaotic Eclipse publicly warned Microsoft, saying, "The fire will go as long as you want unless you extinguish it or until there is nothing left to burn." And they are actively teasing a, quote, big surprise for the June 2026 Patch Tuesday.
Right, which highlights the real friction in the vulnerability disclosure ecosystem. But, we cannot let the drama distract from the infrastructure threat, especially because Yellowkey isn't the only fire burning in the BitLocker space right now.
True.
A French cybersecurity firm, NGINX, just detailed a totally separate attack chain.
Yeah, this is the BitLocker downgrade attack leveraging CVE 2025-48804. It's a CVSS 6.8. And I was reading through their report, and they claim an attacker can use this to bypass BitLocker in under 5 minutes.
Under 5 minutes, yes.
But wait, Microsoft patched that specific CVE back in July of 2025. So how is a patched vulnerability from a year ago bringing down systems today?
Well, it's because of a massive blind spot in how Secure Boot handles legacy trust. Secure Boot's entire job is to verify the digital signature of the boot manager before loading the OS.
Right.
NGINX realized that an attacker can simply bring an old, vulnerable version of the Windows boot manager, the bootmgw.efi file, and just force the system to load it.
But why does Secure Boot allow an outdated, vulnerable file to run? Like, shouldn't it check the version number and just reject it?
You would think so, yeah. But it doesn't. Secure Boot primarily checks the certificate. Yeah. The vulnerable boot manager from 2025 is still cryptographically signed with Microsoft's old PCA 2011 certificate. The system looks at the signature, confirms it legitimately came from Microsoft, and just lets it run.
Unbelievable.
And from there, the attacker feeds the vulnerable boot manager a modified blob table. The boot manager checks the integrity of the legitimate Windows image, but the modified table simultaneously forces it to boot from a secondary, attacker-controlled image that's infected with a command shell.
See, I have to challenge the severity of this, though, because both the Yellowkey vulnerability and this intrinsic downgrade attack, they require the attacker to have physical access to the machine, right?
Yes, they do.
They have to physically plug in a USB. If a threat actor is already sitting at a server rack with a thumb drive, hasn't the listener already lost the security game? Like, why is this a 5-alarm fire?
So what's fascinating here is that is a very common assumption, but it entirely misunderstands the threat model BitLocker is actually designed to address.
Okay, how so?
The fundamental premise of full disk encryption is that physical access should absolutely not equal access to the data.
Right.
Consider stolen corporate laptops left in airports, or servers sitting in branch offices where physical security is essentially non-existent. If physical possession guarantees instant decryption, your data privacy relies entirely on just the plastic shell of the laptop.
Yeah, that makes total sense.
BitLocker is supposed to be the cryptographic fail-safe when physical security fails.
That reframes it perfectly. The physical lock on the door is broken, so the safe inside needs to hold up.
Exactly.
So, practically speaking, what is the takeaway here? How do administrators lock this down today?
For the downgrade attack, the fix is administrative but kind of tedious. You need to migrate your boot manager to the newer CA 2023 certificate and explicitly revoke the old PCA 2011 certificate in your UEFI databases.
Okay, update the certs.
Right. But for the broader defense against both of these bypasses, and frankly any future WinR bugs, the absolute most critical step is enabling a BitLocker PIN at startup.
So pre-boot authentication.
Yes. A PIN stops the boot process entirely before these automated environments, including the recovery partition and the boot manager, can even load into memory.
It just severs the attack chain at the root.
Exactly.
Require a PIN before the OS even thinks about waking up.
Yeah.
All right, so we are seeing how trusting the physical perimeter completely fails Windows. But what happens when the perimeter isn't physical, but a local user boundary.
Yeah, that leads us straight to the Linux kernel.
Right. We are seeing that exact same misplaced trust right now tearing through Linux. We're moving from physical subversion to local privilege escalation, or LPE.
And we are talking about a vulnerability codenamed Fragnesia.
Fragnesia, yeah. Tracked as CVE 2026-46300. It carries a CVSS score of 7.8, and it was discovered by William Bowling from the V12 security team.
Who does great work, by the way.
Oh, absolutely. So this bug lives in the Linux kernel's XFRM, ESP, and TCP subsystem. What exactly does that subsystem do, and how is it being optimized?
So XFRM is basically the IPsec framework in the Linux kernel. It handles secure network tunnels and payload encapsulation. ESP and TCP specifically allows encapsulating security payload packets to be sent over standard TCP connections.
Okay, so it's a highly complex networking component.
Very complex. But Bowling discovered a logic flaw in how this subsystem interacts with memory management. This flaw allows an unprivileged local user to corrupt the kernel page cache.
And the page cache is how Linux maps files from the hard drive into RAM to speed up performance, correct?
Exactly. Instead of reading from the slow disk every single time you execute a program, the kernel keeps a copy in lightning-fast memory.
Right.
What makes Fragnesia so devastating is that the attacker uses this networking logic bug to overwrite read-only files that are currently mapped in the page cache. Specifically, they target the /bin/some binary.
Which is the program used to switch user accounts.
Right.
So wait, they aren't actually altering the so file on the hard drive itself. They are altering the kernel's memory of what that file is supposed to do.
Yes, exactly. They corrupt the cached version of the binary with their own payload. When this system executes the suck command, it pulls the corrupted logic from RAM and instantly grants root access.
Wow.
And what makes this bug stand out from previous vulnerabilities is that it does this deterministically.
I've seen researchers referencing this as a time of use bug or a toss to you vulnerability. How does that mechanism actually play out in memory?
So a toss to you bug is essentially a race condition, but think of it like a classic bait and switch.
Okay.
For the listener, imagine a bouncer at a club checking your ID. He looks at your ID, verifies you're over 21, and hands it back.
Oh.
In the split second between him handing it back and you stepping through the door, you swap places with an underage friend.
Oh, I love that analogy.
Right. The system performed the check, but by the time the system executed the action, letting the person inside the actual state of reality had changed.
So the Linux kernel checks the permissions of the original file, approves it, but before the CPU actually executes the instructions, the attacker uses the XFRM bug to swap the cached memory pages with a malicious payload.
Precisely. And, this is the third major kernel bug of this specific type in just 2 weeks following Dirty Frag and Copy Fail.
That's a lot in 2 weeks. But I do have to play devil's advocate here.
Sure.
There is no in-the-wild exploitation of Fragnesia yet, right? And as we established, it requires a user to already have local access to the machine. They need a foothold first.
That's true.
So should administrators really be dropping everything to fix this today? Like, is this an emergency, or can it wait for a standard patching window?
Well, if we connect this to the bigger picture, to understand why administrators need to patch this immediately, we need to look at the cybercrime underground economy.
Okay.
ThreatMun just published a report observing a threat actor known as Burzioa selling a different Toastio Linux LPE 0-day on an exploit forum. Do you know the asking price for that local privilege escalation bug?
Oh, man. I don't even want to guess. What is it?
A whopping $170,000.
170 grand. Wait, really? For a local bug?
Yeah.
Is that price tag artificially inflated by the forum, or is that actually the going rate for root access these days?
That is actually the going rate. And it proves how incredibly valuable reliable LPEs are to modern threat actors.
Wow.
I mean, we tend to focus obsessively on the initial breach, phishing emails, compromised credentials, exposed web apps.
Right, getting through the front door.
Exactly. But initial access often only gets the attacker a low-level restricted shell. To actually monetize the breach, to deploy enterprise-wide ransomware, exfiltrate protected databases, disable security telemetry, they absolutely need root access.
It's the critical second step.
Reliable privilege escalations are the mandatory second step in almost every major ransomware deployment. If you leave Fragnesia unpatched, you are handing them that second step for free.
You're doing the hardest part of their job for them. Okay, so the takeaway for the listener is obvious. Patch immediately. Advisories are already out for Alma Linux, Amazon Linux, Red Hat, Ubuntu. But, in enterprise environments, rebooting core Linux servers isn't always possible on a Thursday afternoon.
Definitely not.
What is the mitigation if patching just isn't an option today?
Well, you can apply the exact same mitigations that work for the dirty frag vulnerability.
Okay.
The goal is to cut off access to the vulnerable subsystem entirely. So, disable the SP4 and SP6 kernel modules, disable the related XFrem and IPsec functionality if your architecture doesn't absolutely require it for tunneling.
Good to know.
Furthermore, cloud security firm Wiz noted that AppArmor restrictions on unprivileged user namespaces serve as a strong partial mitigation. If you have AppArmor configured, enforce those boundaries aggressively.
All right, so to summarize, physical access is bad, local access is worse.
Yeah,
But the absolute holy grail for an attacker, and literally the worst case scenario for the listener, is unauthenticated remote access.
without a doubt.
And that brings us to a time bomb that has been ticking since 2008.
Yes, NGINX Rift.
Yeah.
I mean, if you want a masterclass in the absolute terror of legacy trust, this is it.
It's just wild. The vulnerability is CVE 2026-42945. It boasts a CVSS score of 9.2, and it impacts both NGINX Plus and NGINX open source.
Right.
It was discovered by a researcher named Depth First. And we are talking about a heap buffer overflow in the NX_HTTP_rewrite_ module. And the most staggering detail, it went completely undetected for 18 years.
18 years. I mean, that code was written before the first iPhone was released.
That puts it in perspective.
It has been sitting inside one of the most widely deployed mission-critical web servers on the internet for almost 2 decades.
So what is the mechanism here? How does an attacker trigger a heap overflow in a web server just by sending traffic?
It all comes down to how NGINX parses highly specific configuration directives. To trigger the vulnerability, an attacker just sends a crafted HTTP request. But the server itself must have a specific configuration.
What kind of configuration?
It happens when a rewrite directive in the config is followed by another rewrite, an if statement, or a set directive. And crucially, the rewrite rule must use an unnamed PCRE capture, like $1 or $2, and the replacement string must contain a question mark.
Okay, let's break down what is actually happening in the C code there. What does a simple question mark actually do to the parsing logic that causes the memory allocation to fail?
So in URI rewriting, a question mark is not just a character. It's a structural delimiter that signifies the start of query string arguments.
Okay, makes sense.
When the NGINX parser sees that question mark, it flags a specific memory sizing function to handle the arguments. However, when you combine that state change with an unnamed regular expression capture, it creates a fatal desync in the logic.
Ah, desync.
Yeah. The system allocates a specific chunk of heap memory based on one assumption of the string's length, but the copy function pulls bytes directly from the attacker's raw URI, which is much larger.
So the attacker realizes the allocator set aside, like, 50 bytes, but they use the URI to force the system to copy 500 bytes into that space.
Exactly. The bytes bleed past the allocation, overflowing the heap. And because those extra bytes are derived directly from the attacker's URI, the memory corruption isn't random. The attacker carefully shapes the overflow.
Oh, that's clever.
If address space layout randomization, or ASLR, is disabled on the host OS, the attacker can use that structured overflow to achieve direct remote code execution, RCE.
And if ASLR is enabled and the memory layout is randomized?
Then the attacker simply sends repeated, malformed requests. The overflow crashes the memory space and keeps the NGINX worker processes in a continuous crash loop.
Which results in a denial of service.
Exactly, a devastating DOS.
Mm.
And remember, it requires zero authentication. No prior access, no existing session cookies. The attacker just sends an HTTP request to the web root, and the infrastructure falls over.
Here's where it gets really interesting, though. It's like finding a catastrophic structural flaw in the foundation of a skyscraper 18 years after everyone moved in.
That's a great way to put it.
But I have to ask how this is even possible. NGINX is arguably one of the most scrutinized, heavily audited pieces of software on the planet. Millions of enterprise servers run it. We have sophisticated, automated fuzzing, bug bounties.
Yeah, all of that.
How does a 9.2 CVSS flaw sit in plain sight for 18 years without anyone noticing?
Well, this raises an important question about the paradox of legacy code. When code is new, it gets heavily scrutinized. But once a module has been running in production for a decade without causing massive outages, it gains this dangerous aura of invulnerability.
It becomes a black box of trust, like it works, don't touch it.
Precisely. Human security auditors inevitably focus their limited time on the new features, the shiny new modules, the modern API integrations. Legacy code just gets a free pass simply because it has survived this long.
And what about the automated fuzzers? Why didn't they catch it?
Parsing logic, especially involving regular expressions in URI rewriting, is notoriously complex to fuzz. Automated fuzzers throw random or semi-structured garbage data at an application to see what crashes. But this vulnerability required a highly specific configuration state on the server, combined with a highly specific syntax arrangement of unnamed captures and delimiters in the request.
So it was just too specific for a random fuzzer to stumble upon.
Exactly.
Yeah.
It wasn't that the code was obviously malformed. The conditions to trigger the desync were just weird enough and deep enough in the logic tree to entirely evade fuzzers that didn't know the exact shape of the key required to open that specific door.
It was hiding in the sheer complexity of edge cases.
Yeah.
So what are the takeaways for the listener here? Obviously, updating NGINX immediately.
Yes, the patched versions were actually released quietly after responsible disclosure. So update your NGINX open source or NGINX Plus instances immediately. But if patching is impossible right now, the mitigation is incredibly specific but simple.
How do you manually block an 18-year-old memory leak without patching?
You audit your NGINX configuration files. Look for every single rewrite directive. If your developers are using unnamed captures, those $1, $2 variables, you need to change your rewrite configurations to use named captures instead.
Oh, wow. Just change how you name the captures.
Yeah. The memory allocation desync vulnerability only triggers when evaluating the unnamed captures. By explicitly naming your rejects captures in the configuration, you force the parser down a completely different, secure code path.
Wait, really? Changing a $1 to a named capture in a config file saves your entire perimeter from an unauthenticated remote code execution flaw.
It really does.
That is the definition of a high leverage fix. All right, we have covered a massive amount of highly technical ground today. Let's distill this into a rapid-fire recap of the practical impacts for you, the listener.
Let's do it.
First, on the Windows front. Lock on BitLocker with a pin in at startup and update your certs to kill that downgrade attack. Second, for Linux, patch those kernels to stop page cache corruption or apply the dirty frag mitigations if you can't. And third, update NGINX or fix those unnamed rewrite captures immediately.
And as we wrap up, I want to leave you with one final thread to pull on. Today, we saw a trusted Windows certificate from 2011 used to bypass encryption and an NGINX module from 18 years ago used for remote code execution.
Yeah, both legacy components.
As we rush to build the future of our digital infrastructure, how much of it is standing on an inherently decaying foundation of legacy code? Are we actually securing our future, or are we just waiting for the past to catch up with us?
Oof. A perfectly unsettling thought to leave us with. Thank you for joining us on today's deep dive. Stay curious, stay secure, and we will catch you next time.